So here's the problem. We've said that we can't tell if we're moving. There's no absolute frame of motion, but we have the speed of light that is always the same. Now, how do those two things conflict with each other? Well, let's imagine that there are two of us and I'm on a boat and I'm going to this direction, whereas you're stationary. You're sitting there on the quay side. Yes. Okay. Now, let's say you shine a torch that way, and that light from that will go out at 300,000 kilometers a second. But let's say as I come along here, shine a beam of light past you, and I'm moving towards you at, say, 1 meter per second. What speed is that light going to be going at when it goes past you?
Well, intuition says it should be going your velocity plus the velocity of light. So if you're going 1 meter per second, then it'll be 300,000 kilometers per second plus your 1 meter per second. And that means that if we shoot our torches off at the same time,
mine's going faster than yours.
Your light's going to pass my light.
Yep, so that conflicts with this equation we just had back here, which said it was that speed. It didn't say where it was launched from, it just said that speed. So we're now violating Maxwell's equations. And it'd be really bad if, for example, I was going along at the speed of light and shining a torch backwards. Because then as I came past you, I'm going at 300,000 kilometers a second that way, I'm shining light backwards. So what speed would the light be then going past you?
It would just be stuck there. That would be a pretty cool theater trick.
Yeah, just a frozen light. But that can't work, because remember, what produces a magnetic field is a changing electric field. What produces an electric field is a changing magnetic field. So if it's just sitting there, it's not changing.
Yeah, so that would be problematic, but...
So they have to move to exist.
So, you know, to give some people some intuition, you know, I grew up in Alaska. In Alaska, one of the things you do is you get in snowball fights. Now, I had an okay arm, but not a great arm, so I could only throw a snowball at about, maybe 50 kilometers an hour. But one of the tricks we used to use is we'd get in the back of a pickup, that is a car that has a open backside, and we'd drive along the road at maybe 50 kilometers an hour, so that when I threw my snowball at you, it would go 50 kilometers an hour that I could throw, plus the 50 kilometers an hour of the car. So it certainly works for snowballs, because trust me, a 100 kilometer an hour snowball hurts a lot more than a 50, and this trick really did make the snowballs travel a lot faster.
So we've kind of got a choice here. So one possibility would be that exactly the same thing that works for snowballs works for light. That if I'm going fast and I shine light forward, it'll go faster. So in that case, we've violated Maxwell's theory. We've said that light doesn't always travel at the same speed. It can go faster or slower depending where it gets launched, and it could be stationary. Einstein's famous thought experiment was to fly a spaceship alongside a light wave, and it would be stationary, which it can't happen because electromagnetic waves have to move to work. They have to move at that speed to work. So that's one problem. But maybe it's not like that. Maybe when I'm running forward and I shine my torch, instead of going at 300,000 kilometers a second, it goes at 300,000. Instead of going at 300,000 plus 1, it just goes at the same speed. No matter, even if I'm running at half the speed of light, it doesn't go at 1.5 times the speed of light. It still goes at 1 times the speed of light, because it's always going at the same speed relative to some universal frame of reference.
Okay, but that means that if I'm in let's just say I'm in a box or I'm in this room, and we know, for example, the Earth is traveling at 30 kilometers per second around the sun. So let's say the Earth's motion's that direction. Mm-hmm. That means that if I shine, a torch that way, and I measure how fast light moves that way, and I measure how fast it goes that way, I should be catching up or going behind it. So it travels the same speed, mm-hmm. but I'm moving, and so I should be catching up or with the light, at least, in one direction. I should be able to see it. Yeah. I should see a different speed of light if I'm in a box.
So you've got a paradox. There's a conflict between Galileo's idea of relativity that there's no absolute frame of reference and Maxwell's idea that electromagnetic waves. And there are two possibilities. One is that when you shoot light, it goes out at your speed plus its own speed, in which case Maxwell's dead because light can go at different speeds and can even be stationary. The alternative is to say that light always goes at speed with respect to some sort of fixed background. In that case, Galileo's wrong, because we can then run around, even in a locked box, and find if we're moving by sending light into different directions and seeing how fast they go. So one or other of these has to be wrong.
Yes, well, okay. I always believe that when it's kind of hard to tell, the best thing to do is to do an experiment. But It doesn't seem to me why Galileo might not be wrong or why Maxwell might not be wrong. I mean, reality is going out and looking.